In the 1930s, America, the idea of spanning the Golden Gate Strait seemed impossible. The strait's swirling currents, powerful tides, and dense fog presented daunting challenges, and skeptics dismissed the notion of a bridge as too costly and ambitious. Yet for San Francisco, isolated at the tip of a peninsula and reliant on unreliable ferries, a bridge was essential. It would not only connect communities, but transform the region's economy and identity. The turning point came with engineer Joseph Strauss, whose bold vision for a bridge over the nearly 2-mile expanse pushed the boundaries of engineering. Though his initial designs were impractical and ridiculed, Strauss persisted. Collaborating with engineers like Leon Moisseiff and architect Irving Morrow, he refined the concept into a sleek suspension bridge, both functional and iconic. By the late 1920s, the project gained momentum despite fierce opposition from ferry operators, environmentalists, and skeptics. The Great Depression added further obstacles, making funding seem impossible. But Strauss and his team secured bonds backed by the people of San Francisco, a gamble that would forever change the city and the region. The design of the Golden Gate Bridge emerged from necessity and evolved through innovation, addressing the site's natural challenges and the engineering limitations of the era. Early proposals included cantilever and hybrid cantilever suspension designs, like those from Joseph Strauss. While structurally sound for shorter spans, these lacked the efficiency and elegance required for the Golden Gate Strait's 1.6-mile span, with its deep waters and powerful tidal currents. The sheer scale of the project demanded a more sophisticated solution: a full suspension bridge. Suspension bridges are ideal for long spans, efficiently distributing loads through vertical cables attached to a main cable anchored at both ends. This system transfers the deck's weight to towers that bear vertical loads, while horizontal forces are absorbed by anchorage points. This design eliminated the need for intermediate supports, impossible in the Golden Gate Strait, where waters reach depths of 372 feet, and construction is challenged by fast-moving tides and unpredictable weather. The Golden Gate Bridge adopted a 2-tower suspension system with a central span of 4,200 feet, making it the longest of its kind at the time. The 746-foot towers were engineered to endure vertical and horizontal forces, incorporating a steel truss system to stabilize against lateral pressures like Pacific winds, which can exceed 60 miles per hour. This truss also counteracts torsion, the twisting motion that could destabilize the bridge under uneven loads, such as traffic or thermal expansion. The use of suspension cables made from parallel wire strands, rather than single thick cables, was a key innovation. Each cable, composed of 27,572 individual wires forming a diameter of 36 inches, provides immense strength and redundancy. Damage to a single wire does not compromise the entire cable. The cables were spun on-site using a continuous process to ensure precise tension and alignment across the span. The bridge's deck, supported by stiffening trusses, was designed to mitigate wind-induced and weight-induced oscillations. Its streamlined profile reduces wind resistance, critical for its exposed location. Vertical suspender cables, carefully tensioned, distribute the deck's load evenly, accommodating dynamic forces like earthquakes, a major concern in Northern California's seismically active region. Alternative designs, such as arch bridges or continuous trusses, were considered but deemed impractical. An arch bridge would have required massive piers in the strait, an unfeasible solution given the depth and tidal conditions. Continuous trusses, though strong, would have been prohibitively expensive and lacked the aesthetic appeal necessary for a landmark. The suspension bridge design offered the perfect blend of functionality, cost efficiency, and visual elegance, befitting San Francisco's iconic gateway to the Pacific. In theory, the entire system works as a dynamic equilibrium. The weight of the deck pulls downward, the main cables pull outward, and the towers and anchorages resist these forces. This constant balance allows the bridge to remain stable under changing loads and environmental conditions, ensuring its durability against time and nature. Every element, from the shape of the towers to the tension in the cables, was a deliberate choice, reflecting a deep understanding of both physics and the challenges posed by the Golden Gate itself. Safety was a paramount concern during the construction, and Joseph Strauss took unprecedented steps to protect workers, a rarity in the 1930s. One of his most notable innovations was the use of a safety net, which was strung underneath the bridge from end to end during critical phases of the construction. Made from manila rope and reinforced with steel, the net saved the lives of 19 men who fell into it. These men later called themselves the Halfway to Hell Club. While the net significantly reduced fatalities, it wasn't foolproof. On February 17, 1937, a section of scaffolding collapsed, plunging 10 workers to their deaths. Despite this tragedy, the project's safety record was far better than similar undertakings of the era. Workers were also required to wear hard hats, which were still a relatively new concept at the time, and they were given glare-resistant goggles to combat the harsh sunlight reflecting off the water. To address the physical demands of the job, Strauss implemented regular safety briefings and encouraged breaks, particularly during heat waves when metal surfaces could become dangerously hot. One of the key machines used during construction was the derrick crane, a large, powerful device designed to lift heavy loads, such as steel sections and concrete blocks, into place. These cranes were mounted on barges for transporting materials and later installed on the bridge towers themselves, allowing them to operate at great heights. Compressed air caissons were used to lay the foundations for the towers. These watertight chambers allowed workers to dig deep into the seabed while keeping out water. Inside the caissons, laborers worked in high-pressure conditions to anchor the towers securely, a process fraught with dangers such as decompression sickness, or the bends. The construction followed a carefully planned sequence, starting with the towers, which were built on massive concrete foundations laid on either side of the strait. Once the towers were completed, the main cables were spun using aerial spinning techniques. This involved threading thousands of wires back and forth across the strait, gradually forming the massive cables that would suspend the roadway. The bridge was indeed built from the middle outward, a standard practice for suspension bridges. This approach ensured that the structure remained balanced as sections of the roadway were added. Building outward from the center also allowed engineers to take advantage of the cable's natural sag, which helped stabilize the roadway as it was installed. The process began by suspending temporary catwalks from the main cables, providing a platform for workers to assemble the bridge deck. From there, sections of the roadway were lifted into place, bolted together, and welded to create a seamless span. The Golden Gate Bridge's steel components expanded and contracted with changes in temperature, presenting a significant challenge during construction. To address this, engineers included expansion joints in the design, which allowed the steel to flex without compromising the structural integrity of the bridge. These joints absorbed thermal stresses, ensuring that the bridge could withstand the extreme temperature fluctuations common in the Bay Area. Concrete, which was used for the foundations and anchorages, also posed challenges in the heat. Strauss insisted on using a special curing process to prevent cracking. Workers kept the concrete cool by spraying it with water and covering it with wet burlap during hot days, ensuring even drying and reducing the risk of thermal expansion. The Golden Gate Bridge, completed in 1937, is more than a transportation link. It's a symbol of human ingenuity and determination. Once the world's longest and tallest suspension bridge, its bold Art Deco design and vibrant international orange color made it an iconic gateway to the Pacific and a lasting emblem of San Francisco. Beyond its engineering marvel, the bridge shaped California's identity, connecting communities, fostering trade, and attracting millions of visitors. Designed to endure earthquakes, fierce winds, and time, it remains a lifeline for the Bay Area and one of the most photographed landmarks in the world, embodying resilience and progress. Enjoyed this look at the Golden Gate Bridge? Subscribe to Atlas Cove, and join us for more incredible engineering stories. See you in the next video.